Wait, so the random, can you just lower it a little bit because I have the return of the sound and yes. Okay. I think it's better. Yes. Okay. Ça va. So yesterday we saw the trap model, the REM-like trap model in detail. I didn't have time to finish and state the result about the correlation function, but I will not do it. And today, for the random hopping dynamics of the REM, I will start by stating all the results. So we see the results, the full set of results for one model completely, and then at the end I will start discussing the proof, and we will continue discussing the techniques of proof tomorrow in the PaySpin, in the random hopping dynamics of the PaySpin SK model. So let me remind you what the model is. So the state space Vn is the n-dimensional discrete cube minus 1, 1 to the n. The graph is the set of edges of Vn. So we have a sequence of graphs indexed by n, an integer. The Hamiltonian of the random energy model is a Gaussian process indexed by the vertices of the hypercube. It is a centered Gaussian process with simple covariance metrics. The covariance between h and x and h and y simply is n if x and y are an edge of the cube. The twiddle symbol here denotes nearest neighbors in the cube, and it is 0 else. So in fact, this is a collection of independent and identical Gaussian random variables centered with variance square root n. The dynamics is denoted xt. It is a continuous time Markov jump process on Vn. And by now, we are used to describing this law using the joint law of its jump chain. And I said x twiddle. Twiddle means they are nearest neighbors. Equal, sorry. You're right. Thank you. So it's 1 n on the diagonal and 0 off diagonal. Thanks. So the law is described through the joint distribution of the jump chain and holding times. The jump chain J and I is a discrete time Markov chain. It is the simple random walk on Vn. So the probability to take a step from x to y is 1 over n if, and this time, if x is a nearest neighbor of y on the hypercube, and it is 0 else. And at each step of the jump chain, the process xn waits an exponential holding time with mean value called tau nx, given by the exponential of minus beta h at x. Here, beta is a positive parameter that represents the inverse of the temperature. And this quantity, tau x, is called the Boltzmann weight at x. So using these, the jump chain and mean holding times, we define the clock. Sn. This is the sum over the first case steps of the jump chain of the mean holding times. So tau n times e, where these little e's are, they are IID, mean one exponential random variables. And finally, so let me call it S tilde because it's the discrete time clock, and we will later introduce the rescaled clock that I will call S. So using the clock, we define the process Xn by first taking its inverse, using it to time change the jump chain, and we get the process Xn. That was the whole idea behind this jump chain and holding time construction. So this follows the global strategy that I explained starting from the beginning. And so we saw in the first lecture that to study aging, we had to choose 3 ingredients. The first was the initial distribution. We will always start the process in the uniform measure. Pi n on the hypercube. So there is a reason for this choice. It is a common choice that comes from the idea in physics of a deep quench. So you first warm up your system at a very, very high temperature. It then gets terribly disordered because temperature is very, very high. And all of a sudden, you bring the temperature down, and the system freezes in one particular state. You call that a deep quench. And what you are expected, the right way to model this is to take a uniform distribution on your state space. So that's why we start from this measure. You will see that the techniques apply for more general starting points, but it's easier for us to just take this one. The second thing we must choose is time scale. I will call it Cn, and I will tell you how we choose it in a second. And the third thing will be, of course, the 2-time correlation functions on which to observe aging. And again, I will, well, we saw how to write it many times already. I will restate it when I come to give the result about this. So let me first start. So at this point, we saw that we had a strategy to control 2-time correlation functions. So the main one we saw so far was this probability pi n, that the process did not jump in a time interval. So this is time measured on scale Cn. The process starts at 0 in pi n, and the 2-time correlation function measures the correlation between the states of the process at these 2 times. The particular correlation function pi n was the probability that no jump occurs in this time interval. And we saw other definitions of the 2-time correlation function that I will come back to later. So we saw that we have a strategy for proving aging of the 2-time correlation function, which is to first prove convergence of the clock process to a subordinator, and then use the self-similar properties of the stable subordinator via Dynkin and Lamberti arc-sine law theorem to get the expected slowdown of the two-time correlation function. So I will first state the result we get for the clock process, and then give you the full statement for the two-time correlation function. So let us start with the convergence of the clock. And I'll now define the timescales so we will say that Cn is called an intermediate timescale if there exists a sequence an such that, so I have three conditions, an times the probability that tau n is larger than Cn equals 1. This P double bar here is the probability space of the random environment, as always in these lectures. So this is the first condition. The second condition is that log of an over n log 2 goes to epsilon. So there exists an and epsilon in 0, 1. And the third condition is that an over 2 to the n goes to 0 as n goes to infinity. So what this tells us is that an is roughly exponential epsilon, 2 to the epsilon n. For some epsilon in 0, 1, strictly positive, but can be 1. So it increases, it grows like exponentially fast, but still it remains small compared to 2 to the n. So if epsilon is 1, then there should be a prefactor that brings this to 0. And we will say that, so this is the first definition, that Cn is an extreme scale if, so the first condition is the same. The second condition is that log of n times log an divided by n times log 2 goes to 1. So this times an behaves like 2 to the epsilon n, but the ratio of an to 2 to the n goes to a constant, epsilon prime, that I will again take in 0, 1. So in this case, an scales like the size of the system, because there are 2 to the n points in the discrete cube. Okay, so we have two different timescales. And as you can guess, because we also had two different timescales yesterday, there will be two different behaviors of the clock on these two scales. I will need a notation. I will define beta c of epsilon to be the quantity square root 2 epsilon log 2. And I will call alpha of epsilon the ratio of beta c to beta. Yes, so you see that this here plays the role of an effective timescale that depends of an effective temperature, sorry. So beta is the inverse of the beta in this definition of the two-time correlation function here is the temperature. And this beta will play the role of an effective temperature. But as you can see, this effective temperature depends on the time scale, on the chosen time scale, Cn, through this definition. Because choosing an like 2 to the epsilon n, the Cn that solves this equation is a function of epsilon n. So this beta here is a effective temperature that depends on the time scale. Now the result we get is the following. So let us first suppose that Cn is an intermediate time scale. Then for all epsilon in 0, 1, and beta larger than beta c of epsilon, the sequence of rescaled clock processes so I will perhaps make this definition here so I don't have to make it several times. So the question we want to answer in this theorem is find sequences An and Cn such that the rescaled clock process Cn minus 1 S tilde n of A and T A and T converges. So S tilde was the discrete time clock. I introduced the rescaled process, and I'm now interested in finding sequences of timescale Cn and the auxiliary associated timescale An that makes the clock converge. So what we get here is that if Cn is an intermediate timescale under these conditions on epsilon and beta, the sequence of rescaled clock processes converges to a limit that I'll call S intermediate. This convergence, of course, is in the set of Cadillac path on Rd. It is weak convergence in the J1 topology, and the limit is a stable subordinator of Levy triple 0, 0 nu. I will call it nu intermediate, and the measure nu intermediate has tau given by alpha of epsilon, gamma alpha of epsilon, u to the minus alpha of epsilon for u positive. And this holds P almost surely in the random environment if An log An over 2 to the n decays to 0 as n diverges, and in P probability otherwise. So what we get is that the limit is a stable subordinator with this exponent, alpha of epsilon. Because beta is larger than beta c, alpha is smaller than 1. So under these conditions on epsilon, epsilon comes from the time scale, and beta, we get a stable subordinator of exponent alpha in 0, 1. the convergence is almost sure, so that's really what we want, almost all the way up to extreme scales, but on the very last time scales before extreme scales, we have a weaker convergence in probability. This comes from technical reasons. Now, what do we get on intermediate scales? On extreme scales. So as yesterday, things will change completely on extreme scale. And the reason for this is that, I explained it a little bit yesterday on the RAM-like trap model. On that scale, the process starts to feel that its state space is finite, and it starts to feel the influence of equilibrium coming. And so this, to see this, I think it will be clear by the end of the lecture, but so let us form so let me call gamma n of x the rescaled variable Cn minus 1 times tau. And let us form the point process, that is the sum of the point masses at x. So this is our point process whose points are the rescaled. And so when I talk about the random landscape, random environment, it's always the same thing. It's the taus. So what we get here is that this process converges to a Poisson point process. With an intensity measure of the form u to the 1 minus alpha du, where alpha is alpha 1. So, this convergence here is unfortunately only a convergence in low. And this convergence in low, we saw already yesterday, was not enough to get a strong convergence of the clock process. And we saw yesterday that when we have a sequence that converges only in low, and we want to make a statement that is stronger, that we want to make a statement that is true almost surely in the random environment, then we go to Skorods representation and find another sequence that has the same distribution but converges strongly. So this is, again, the idea that we will apply here to make the following statement. So let Cn be an extreme scale. Then there exists both the sequences gamma n of x and the points of the limiting point process gamma k can be represented on a common probability space. I'll call it omega f blackboard p bar, such that on that space p bar almost surely and for all beta larger than beta c of 1, the rescaled clock process converges to a limit called S extremo in D, where S extremo is a subordinator with Levi-Triplet 0, 0 nu extremo, and the measure nu extremo is now a random measure that depends on the point process, the points of our point process gamma k. It is the sum from k equals 1 to infinity of minus exponential minus u divided by gamma k. So you are not surprised because we saw exactly the same statement yesterday. And in fact, what is very remarkable is that the statements are so exactly the same. So the clock process in the REM moving under the random hopping dynamics has exactly the same behavior as the REM-like clock process, which is surprising because in the REM-like we have a small dynamics on the complete graph and traps that are regularly varying. The taus are IID regularly varying traps. And now we have a simple random walk on a huge hypercube in evolving in a random landscape given by the exponential of our Gaussian process. They don't seem to have much in common, so why should they behave so much in the same way? And so this is the question we will try to understand in this lecture. But before going into this question, I would like to make the statement for the two-time correlation functions, because otherwise I think we will spend the entire lectures without ever seeing them. So let me keep just the two statements of the theorem and perhaps this. Okay. So I will also erase the clock. So what are the consequences for the two-time correlation functions? So let me add one more result to the extreme time scale. So we see that in the extreme time scale, the limiting subordinator is a random subordinator because its Levy measure is a random measure that depends on the points of our point process gamma that represents the scaling limit of the environment. And this measure is not of the form u to the minus alpha, so it's not a stable subordinator, but it is a subordinator. However, what you can prove is that for all beta larger than beta c, P almost surely, the limit as u goes to 0 plus of u to the alpha nu extremal of u infinity is a constant. So that this tells us that the measure nu is regularly varying at 0 plus with exponent alpha. And we are going to use it in a moment. So let me just perhaps write again the function pi n for those who were not here yesterday or the day before. So this is the probability starting in the invariance measure that the process remains in the same state in the entire time interval t plus s, t plus tw plus s for s in 0t. And we saw that, I told you at least, that this event is the same as the event that the range of the clock does not intersect this time interval. And yesterday at the end of the lecture, I gave you two theorems that tell us what the probability of such an event is in the case where the range here is the range of a stable subordinator or a subordinator. So we saw two results that so they are results that belong to renewal theory, and we saw two of them. The first case was in the case of finite mean renewal. So this is the case where the integral of the measure nu of our subordinator is finite. So this is the finite mean case. And then in the infinite mean case, we saw that this probability for R, the range of a subordinator, was given by the Dynkin and Lampertier-Arcsine law theorem. So we are just going to apply these two theorems to our clocks. And, well, this is what we want to do because we know what the limits are, but we still have to take a limit here. So we just have to be a little careful in taking this limit. So I, of course, want to use a continuous mapping theorem to push the n inside the probability, and I have just to check that this is a continuous mapping. This is not nice to do on this event, but you can use that this event here is the event that the so-called overshoot function. So let me give you the definition directly. It's the first passage time of Sn of in the range of Sn minus Tw larger than T. So these two events are the same, where delta here is the first passage time in the range to the right of Tw. So I can't make a picture really, but suppose that here you have your S. Here is time. So you have your function. You project all the values of S, so you get all your values here. So you get here your range. And you want to know that, so suppose that, that Tw is here. And you want to know that the first passage time in the range after time t, so this is this to the right of t, this is this point, will be minus Tw larger than t. So your process is jumping over the interval Twt. Not sure this is very clear, but this is the idea. So the point is that this function, do you want me to explicitly define it, or do you know what this first passage time function is? Because it's not difficult to define either. So this is Sn at the local time of Sn, where LTW is called the local time, and it's the infimum of T prime positive of Sn T prime larger than TW. Okay, these functions, they are well-known functions in stochastic processes. They are well studied, and we want to know if they are continuous. The answer is that on Skahard space equipped with the J1 topology, as we do, they are not in general continuous. However, if we restrict the space to the increasing and unbounded path, then restricted to that set, the functions are continuous. And this is exactly what we need because our processes have increasing and unbounded path. So for our processes, the convergence of S to S intermediate or S extremo will imply the convergence of these functions. So the convergence of S will imply that S delta TWSN minus TW converges to S TW delta, sorry, my handwriting is getting miserable, S minus TW. So this holds true on the set of increasing and unbounded Cadillac path. So we can safely push the limit inside the probability. And apply yesterday's theorem. So in the case, let me call it of theorem 1, we get, under the same assumptions and with the notation of this theorem, we get that. So we see here that because alpha is smaller than 1, the integral of the tail of the Levy measure is infinite. So we are in the infinite mean case of renewal theory, and in that case we get that phi n converges. So it's not true, it is equal to the arcsine law distribution function with parameter alpha evaluated at TW divided by TW plus T, and this is not an asymptotic statement. It is valid for all TW and all T. So this is a direct application of yesterday's theorem. And now what happens in the case of extreme scale? So well, now we can calculate what the integral of the tail is. So let us do it here. I want to know what the integral of nu extremo u infinity du is. This is the integral of this sum, exponential minus u divided by gamma. And so what I get is the sum of the gamma k. The integral is from 0 to infinity, sum of the gamma k from 1 to infinity. Okay, does this converge? Well, the answer is yes, because the gammas, they are the points of a Poisson point process with intensity measure with tail of the form u to the minus alpha, where alpha, under the assumptions of the theorem, is smaller than 1 because beta is larger than beta c. So this is almost surely finite by Campbell's theorem for Poisson processes. Sorry, finite. So since this is finite, we are not in the case of the arcsine law theorem. We are in the mean renewal case. finite mean renewal case. And then here we can apply the renewal theorem, and what we get is that, so let me write it here. So let me write T as rho TW. So I introduce a scaling parameter, rho, and I will take the limit as TW goes to, I will first take the, here there was a limit, which is n, of course. N goes to infinity. So here I take two limits, n goes to infinity, and t goes to infinity. And what we get, so yesterday's formula was that this limit is the integral from rho tw to infinity of the tail of the measure. Well, if you have the notes, you can read it. So let me just give the results. So it was the integral starting from t to infinity divided by the integral started from 0 to infinity of this thing. And what we get is the following. Sum from k equals 1 to infinity of gamma k divided by the sum of gamma k prime of exponential minus u divided by gamma k. Okay, so this is for u positive. But we also saw yesterday that in the case of the arc-sine law theorem, so in the infinite mean case, that for subordinators, if the tail of the Levy measure is regularly varying, then we do have that taking the limit. Here it is rho. In fact, I don't want to do that. I'm sorry. Let me just write t as it is because, yes, it really is that the process here gets time translation invariance. So it's really just t. I will write t as a function of tw in the second case. Yes. So what we get if we let time go to, if we let the size of the system go to infinity first, but if we now let tw go to 0 plus. We can do this because we have this result that tells us that the tail of the Levy measure is regularly varying at 0 plus. And if you apply yesterday's theorem, you just get that this implies that the two-time correlation function converges again to the arc-sine law theorem of parameter alpha, evaluated at the ratio of the two times, tw plus t, and this is why I need here to write my t as rho times tw, because I want to take this limit. Now, okay, so what this tells us is that the process is aging all the way up to extreme times. And at extreme times, it enters this, it changes regime. So obviously, the process is not here aging. Something is happening at exactly this time, because on that time scale, taking either the limit tw to 0 or to infinity, we get that either the process is aging or is not anymore aging. And then in this regime, the process here enters its stationary regime. So we know that the random hopping dynamics of the RAM is a reversible dynamics. We saw that in the first lecture. We know that it is reversible with respect to the Gibbs measure of the model. And we know that if we start the process in Gibbs measure, it is invariant because it is started in invariance. Now, suppose you start the process in Gibbs measure and calculate your two-time correlation function for the process started in Gibbs measure, then your result you get is exactly this function. And in fact, what you see here is what plays the role of the limiting Gibbs measure. So this is really a description of the process at invariance. So that time scale, the process really begins to feel that its state space is finite. On shorter time scale, it explores its state space and spends time in traps, so in taus, that are of size Cn. When you vary the time scale, you vary the size of the tau, so the traps that the process will see. And when you increase Cn, the process will become slower and slower, explore its time scale, its space case, find deeper and deeper traps. But if you choose the time scale large enough, then there is no more deep trap to be found because it has found all of them. So when the process has found the deepest trap in the landscape, it can't possibly age anymore, and at that time it falls into stationarity. So this is basically what happens. So let me now perhaps show you on the picture the heuristics for the behavior of the clock process, and try and explain just with hand-waving arguments. Yes, we can just move to the... So why is it not there? Huh? Ah, it is. Okay. Can you see it? The resolution is not really good.
It's going to be improved.
Still not very good, is it? Can you read the...
Is it possible to read from the back?
I think you can't read, can you? It is? Okay, good. So I can't, but I can, perhaps I need glasses. So on the first line there, I wrote again the definition of the rescaled clock process on the time scale Cn and auxiliary time scale An. And so this big bowl here is sort of artist's view of a hypercube because I cannot make a picture of a hypercube. So there are two colors, blue and red. I hope that you can see this. So there are blue dots on the picture. These blue dots represent the vertices that are, so in here I wrote the vertices so lambda minus 1 is the notation we had in the first lecture, but lambda minus 1 is just tau. So the blue dots, they represent the vertices that carry taus that are of the order or of Cn. So you see here that if An and Cn obey the scaling relation, then the probability that tau is larger than Cn behaves like 1 over An. 1 over An behaves like 2 to the minus epsilon n. So the set of blue dots on the picture, it is a Bernoulli cloud with probability 2 to the minus epsilon n. So a dot is here or not with a probability 2 to the minus epsilon n. And we have 2 to the 1 epsilon n, 1 minus epsilon n such points. So it's a huge cloud. It's really big. So the red line now, that's represent the trajectory of our simple random walk on the hypercube. So a simple random walk in the hypercube, it typically doesn't revisit points. It takes a very, very long time because it does, before it does so. So I didn't make lots of self-intersections. So the chain, as it walks, it picks blue dots. And to build the clock, it adds all the taus it picks on its way. So I didn't represent the ones that are smaller than Cn, and I didn't represent those that are larger than Cn, because I pretend that only those that are of size Cn will contribute to the clock. Why is it true? Well, first, we know that the mean hitting time of this set of blue dots is of the order of An. So that sounds a little magic because everything fits very well together, but this An is the mean value of the hitting time of the set of points x that carry taus that are larger than Cn. So the proof of this is in one of my joint papers with Hergé Cherny. We gave general hitting times of general sets on the hypercube for huge sets. These times are exponential with a mean value that we give explicitly, and then in the case of Bernoulli clouds with this size, then we get exactly this result. So what does it mean? It means that the red trajectory on its way, it does hit this set, because the length of the trajectory is An. So it is exactly the time it needs to find this set. But it means at the same time that it will never find vertices in the cube that carry larger traps. So all the taus that are larger than Cn, they are never found. So this does with all the larger taus in the landscape. You don't have time to find them because the set of these larger ones is smaller and their hitting time is larger. Now what about the small ones? Because obviously the chain collects lots and lots of taus on its way. It collects actually An taus on its way. What about the small ones? Well, with our choice of the scalings An and Cn here, then what we get is that Cn times the probability that tau is larger than Cn times u behaves like u to the minus alpha of epsilon. So this is the sequential regular variation condition that we saw yesterday. So in the case of the random hopping dynamics of the REM, the taus are not regularly varying variables because they are exponentials of a Gaussian process. But if you look at them with this scaling, then their tails are actually regularly varying with parameter alpha of epsilon. And alpha of epsilon, we saw in our theorem up there that it is smaller than 1. So this is what we needed to make sure that the sum of the small jumps in the clock in our calculations yesterday could be washed out in the limit. So you remember this very last condition we got to make our clock process converge. We had two conditions. One was a regular variation condition that gave us the form of the tail of the Levy measure of the limiting clock. And the other condition was to get rid of the sum of the small jumps in the clock. So to get rid of them, we needed an extra argument that uses that here alpha is smaller than 1. So the result is that the chain walks, and the blue dots are the largest taus that it will pick along its way. And this largest tau will give exactly the leading contribution to your clock, and nothing else will count in the limit. Now, to make the analogy with the REM-like trap model, we need one more ingredient. So we now see why the huge state space can be reduced to a small set of points, why a hypercube could be represented by a simple complete graph, because what matters is a subset, the blue subset of points. Now, why does the process enter this subset uniformly? Because this is what the REM-like trap model does. It jumps from one point to the next uniformly. And actually, a simple random walk does not do that. But the simple random walk, its stationary measure is the uniform measure. So all we have to understand is that the mixing time of the chain is very short compared to the length of the trajectory. It will very quickly, in n2 steps, we will see tomorrow, become stationary. So it will hit the blue cloud from its stationary measure, typically. So typically from the uniform measure. So we now have the heuristics why a complicated random walk on a huge hypercube, why this dynamics can be well represented by the REM-like trap model. So this is the heuristics, and tomorrow we will catch up with the set of tools that we've started to build to prove that. And that will be it for today. Thank you.